L. Boom. Too easy. So yeah, I hope that you liked the former part, because we're continuing on that trend on probability logics in an intuitionistic setting. And so that's a work that's, I mean, this talk was not initially planned, but I decided, I mean, I saw that there was a hole, so I decided to take that hole. And so this was a paper that got published in Tableau recently this year. And so that's a paper that I did conjointly with 3 other people, Rajiv, that you'll see, and also Iris and Rosalie. And so that's about a new calculus for intuitionistic strong Löb logic. And we showed strong termination and cut elimination and formalize everything in Coq. So, okay, so first of all, what is intuitionistic strong Löb logic, which we nickname ISL? It's another probability logic where the box is again interpreted as a probability in a specific theory of arithmetic. I believe that this one is actually the probability logic of heightened arithmetic with what's called the slow probability predicate. Don't ask me what it is. All I'm interested in this logic is that it's quite technical to treat in a proof theoretical setup. But so yeah, the idea again of the probability logic is the GL case as the most canonical one. So on a syntactic side, we just take the full syntax of intuitionistic logic, where top can be defined, but we have bottom, conjunction, disjunction, implication, and we have just the box. Once again, we don't take diamond first, because in a probability setting, the interpretation of diamond is a bit unclear for now, but also because it makes things much more technical. So that's the syntax. For the Kripke semantics, Jim has presented it already. We have a slight variation in the interactions between the intuitionistic relation and the model relation, but that's equivalent in the box setting. Now, the only thing that we add on top is that now the model relation is a subset of the intuitionistic relation. So if you think about persistence, which says that essentially if you travel along the intuitionistic relation, all your formulae will be made true, I mean, will be preserved if they are true at a point, then you know that now in the model relation, this is also holding. So if a formula is true at a point and you travel through the model relation, then all your formulae will be true as well afterwards. So and so from a syntactic perspective, we have 2 approaches. We can take IK box that Jim presented also before, on which you can add this strong Löb logic axiom, which is a slight variation of the GL axiom that you can see just below. Essentially, you just destroy the 2 boxes in the incident and consequence of the implication. But there is an alternative axiomatization, which is just take IK GL axiom, plus you have this very weird axiom, the completeness axiom, that says that phi implies box phi. Note that in the classical case, it sort of trivializes the box, but in intuitionistic case, that's still you still get into interesting properties. So that's what it is from a axiomatic, semantic, and syntactic point of view. But how do we treat this logic from a sequent calculus point of view? Well, I mean, we have calculi for GL, we have calculi for intuitionistic logic, so we could sort of take an intuitionistic calculus and then add the GL rule and try to make it ISL-like. So that's what we're doing initially. So you can just take your intuitionistic calculus with your rule for implication left, which this calculus will then admit contraction. And note that there is a repetition of the principal formula in the left-hand side of the left premise. So you copy it over in order to have contraction admissible. And then you ensure completeness. And we take the GLR rule. So for those who are not particularly familiar with the sequent calculi for GL, what you do is you take the box phi formula on the right, and what you sort of do the normal modal step, which corresponds to travel along the modal relation, which will tell you that box phi on the right means that box phi is false. So there must be a successor where phi is false as well. So that's why the phi on the right is generated. But also we have our box gamma on the left, meaning that box gamma was true at the point where we were before. And so by doing a modal jump, all the formulae in gamma needs to be true. So this is why we generate the gamma on the left there. But we're also in a transitive logic. So then if we did another modal jump, we would have to again unfold the gamma and tell that the gamma is still true. So this is why we preserve also the box gamma going upwards in a rule. And the only thing that I haven't explained yet is the box phi on the left hand side of this of the premise. And that's pertaining to the converse well-foundedness, because the idea of jumping on the modal relation and jumping to another world can now be more generalized, be made more specific in the case of converse well-foundedness, because you can always say, let's jump to the last point where phi is being made false. So then the last point where phi is being made false, all the successors will necessarily be making box phi, will be phi points. So box phi is then true at the point which you pick here. So this is why we have the box phi on the left, which is now made true. And so this formula is called the diagonal formula because it switches polarity from the conclusion to the premise. And that makes our life quite hard in a proof theoretic setting, essentially. So that's what we get. So this is the GL case. But now that we have that the modal relation is a subset of the intuitionistic relation, we need to have this persistence being mimicked in our rule, right? So what we do is we initially deleted all of the big phi. We just destroyed it because we did a modal jump and we don't know what can be preserved across the modal jump apart from the modal formulae. But now that we have persistence, we need to ensure that all these phi formula are preserved in the modal jump. So we just copy them across. And so this is just a calculus for ISL. So that's all good. It's sound and complete, but it has some bad properties to an extent because of two main reasons. First of all, from a proof perspective, at least, first of all, we have that there are intuitionistic loops. What I mean by this, if you can see the intuitionistic implication on the left rule, you could reapply it as many times as you want in the left branch. And so you could have infinite branches if you wanted to. So you could reapply it as many times as you want, and that's not so good for proof search. And also the GL case, the provability logic side of things is also known to be quite complicated in terms of proof search, because you can also create loops. If you look at the bottom sequence, then we apply the modal rule, and the modal rule allows you to unfold whatever box formula was on the left, but you also preserve this box formula. So what that means is that you will eventually be able to re-unfold it, and reuse the same elements again and again. And so we have modulo weakening, we have the same sequence on top. And so we could reapply exactly that cycle that's depicted again and again and again. So we have also what I call transitive loops. And also it's quite well known that the provability logic are usually very hard to treat in a proof theoretical setting. So cut admissibility is known notably to be very hard. So we're trying to tackle all this and get a better sequence calculus, pretty much. So that's what we're doing. We're defining the G4 ISLT, T for terminating, which is a calculus which doesn't have the transitive or intuitionistic loops. And we actually make a more formal claim by showing that backward proof search strongly terminates. I will tell you what strongly terminates means, but essentially we have a measure that decreases step by step in the rules of the sequence calculus along a well-founded order. And we show that not only cut is admissible in a local way, so in a structural proof theory way, and so as a consequence, we get that cut is effectively eliminable. So we have an algorithm that effectively eliminates cuts. And we formalize everything in Coq, so we can actually extract from our Coq formalization a program that takes a proof that contains cuts and which outputs a proof that has no cuts in it. Okay, so first step, let's construct the calculus. So we want to get rid of the intuitionistic loop, and we want to get rid of the modal loops. So first, let's do the intuitionistic one. So this is quite well known that you can get rid of the implication left rule, which was quite problematic, by breaking it down in several rules. So this is a calculus that has been reinvented several times by Dikov, Udelmayer, Vorobev, and others, I believe. And the idea is to destruct that rule and replace it and get rid of the implicit contraction in that rule, you look at the principal connective of the antecedent of your implication, which is on the left, and then you generate one rule for each connective. So for example, here we have the conjunction, and the conjunction then gets transformed into an implication. And so that gives you some sort of termination. I will explain a bit more. But so we have the same for the disjunction. Then we get two smaller formulae according to a certain weighing of the formulae. So notably, you can guess that if you want to get termination and the fact that eventually you will just stop in the proof search, and which is a property that this calculus has, we have to have that the conjunction, say, weighs more than an implication, because essentially then you have that the conjunction on the left formula there is actually bigger than the one in the premise. And so that's a very well-known trick. So if you want to do this for this intuitionistic SL, sorry, we can think about doing exactly the same. Now, this is what my co-authors Iris and Rosalie did in 2020, I believe. And so they generate a model. They generate a model rule because now that we need to, we're in that setting where we're looking at the principal connective of the antecedent of the implication. We need to do the same with the box. We need to generate a rule for the box on the left. And so this is what we're doing. This is the rule that we generate. Now this rule is on the right hand side. You have the usual implication on the right, implication on left, right premise. And the left premise, which is a bit complicated, has very much a modal rule flavor. You can think about it as if we did the box phi, we put it on the right, and then we applied a modal step. Now the problem is that we're trying to kick out the implicit contraction in the rule, kick it out of our setup, but it strikes back because in this case, we need actually to port the implication on the left at the cost of being incomplete otherwise. So if we do not have this implicit contraction, then we just lose completeness. And so we're trying to get rid of the implicit contraction, and actually comes back through the modal rule. So that was the setup. So it sounded a bit bad potentially, but in the end we can still find, despite this implicit contraction, we can still find a terminating strategy, which is rather simple, which is just saying, do not apply a rule on a sequence if it's an identity. If you have phi on the left and phi on the right, just don't apply the rule. And we get termination of proof search in this way. So we have one strategy which terminates, and we want to do better. So this was the setup before we started our work with the four of us. But what we decided to do is try to get rid of this implicit contraction. And in fact, we also got rid of the loops that we got through transitivity in our new calculus in the following way. So we can get rid of transitivity because once again, the modal relation is a subset of the intuitionistic relation, right? So the reason why we were keeping this box gamma in the premise before was to make sure that, hey, if we do another modal jump, then we'll have to remember that we still need to unfold gamma and provide the logical power of gamma in this new world that we're reaching out to. But the thing is, if phi is not ported, phi on the left is now ported in the premise. So that means that through persistence of the intuitionistic relation, the modal relation also has the persistence to an extent. So we don't need to remember every time that box gamma needs to be unfolded somehow intuitively, in the sense that once box gamma is unfolded, once the logical power of gamma will stay in this sequence forever. So we don't need every time to sort of unfold it, so we can just get rid of it. And so this is our new rule, our new modal rule that we call SLTR, which is just doing that and getting rid of transitivity, and that's relied on the fact that a modal relation is a subset of the intrinsic relation. And so how do we get rid of the implicit contraction? Well, if we have a closer look, which is exactly what I highlighted there, we have a modus ponens type of situation in our rule. So we have the implication and the left-hand side of the implication. So why not just simplify this and just do the modus ponens locally and just take psi on the left-hand side? And actually, this does work. This is now a sequence calculus for ISL. And we got rid of the transitive loops in the model case, and we got rid of the intuitionistic loops through implicit contraction. So we haven't proven anything yet, but you can sort of feel that there is termination in the air. So let's get to it, actually. And I want to give some definition here. So in backward proof search, we said that a strategy is just a restriction on the application of rules of a calculus. So there are a lot of strategies. For example, I talked about do not apply the rule if you're in front of an identity. So that's one, but you have many more. You could say don't apply the rule if you're on a Tuesday. Don't apply the rule if it's past midnight or something like this. There are infinitely many. And so we said that backward proof search weakly terminates if you can provide at least one strategy which terminates. And sort of dually, we can say that backward proof search strongly terminates if all the strategies terminate. And this is equivalent to saying that the naive backward proof search, apply any rule in any order you like, is terminating. And this is yet again equivalent to showing that there is a measure that decreases upwards in the rules of your calculus. And that's the latter part that we'll prove, actually. And so, well, once again, let's get to it. And if we want to prove termination for our calculus, we can get some inspiration from the termination arguments for both the intuitionistic part and the modal part. So let's think about the intuitionistic part. Roughly speaking, the intuitionistic termination argument was saying that you have a decrease if you can show that from your conclusion to your premise, you've substituted one or more formulae by one or more formulae of lesser weight, or of lesser measure for whatever measure you have. So, for example, here we swapped the implication on the left in the conclusion for the two ones in the premise, and so the two ones in the premise are smaller, so you have a decrease. For those who know, it's the multiset ordering that you have on finite multisets. Now, this does not work out of the box for our case because of our SLTR rule, because we're substituting box phi by phi and box phi, so we don't have a decrease. We're just staying the same. We preserve the same formula, and actually we somehow not duplicated, but duplicated and then kill a box. So that's not working out of the box. So let's look at what we did for the GL case. It's a bit technical, but roughly speaking, the GL case, you count the number of box formulae on the left. So the more you have, the happier you are, and the closer you are to termination. And the key point was that the box formulae on the left in the GL case are eternal. Once they are there, they cannot be destroyed because of transitivity. But that's exactly what we got rid of. And so then we can't use out of the box either this measure because we're unboxing the left-hand side and not preserve the box formulae themselves. So what do? Well, we'll do something that's very much inspired from the intuitionistic case by doing the same multiset order idea, but before applying the multiset order and checking which formula we swap by which one, we get an insight about the fact that the box formulae on the left are somehow dead weights, because once they are unfolded, nothing happens to them, and then they are useless pretty much to us. So what we do is we just take our sequence, first unbox the left-hand side, and then do the multiset ordering. And then we're in a good situation because we swapped box phi by 2 times phi, which are 2 formulae of lesser weight. And so we're home. So we have that backward proof search strongly terminate for this calculus because we show that there is a measure which decreases along a well-founded order. And so proof theoretically speaking, this calculus satisfies all the properties that you may want. So I'm showing that we have exchange here because in the formalization, we deal with lists our sequence are based on lists and not on multisets because they're handier to work with. But logically speaking, it doesn't really appear. But so we have exchange. We have that weakening is admissible on the left. We also have this quite weird admissible rule, but which again gives you an idea about the fact that the box is pretty much useless on the left, because if you can prove something with the box context on the left, you can prove exactly the same thing without the box. So that's once again supporting evidence for what I claimed before, that box on the left are pretty much useless or dead weights. And we have contraction on the left as well. And so this is the big piece. It's known in a G4IP type of calculus, a la Dikov. It's quite hard to obtain. And we finally get that cut is admissible. And we use the induction as induction measure, exactly the measure that I showed before to show termination. So this is a bit of a tricky proof, but it does work out. And so, yeah, we formalize everything in Coq. So there is our proofs are simply unquestionable. They are mechanically checked. There is no ambiguity. There is no hole. There is no the details is left to the reader. Everything is rock solid. And we proved everything constructive type theory without axioms. And what that implies is that we can actually extract some code which does exactly the elimination of cuts on proofs. Which we haven't used yet, but it's there for whoever wants to use it. And if anyone finds a use for it, please feel free to take it. And the question is, well, I mean, we started from a sequence calculus that had some termination arguments. And then the question is, why did we bother trying to find an even better that strongly terminates? We had already, decidability. So why do we bother about doing this? And the main point is that we're on the hunt for uniform interpolation for this logic, which is not yet known. But for those who are familiar with Pitt's method to show uniform interpolation for intuitionistic propositional intuitionistic logic, well, we have a structurally well-behaving calculus, which has all the proof theoretical properties I mentioned before, which strongly terminates and which is a key element to define the uniform interpolant recursively on a proof search. And so, yeah, we're pretty much within the range of Pitt's techniques. We just need to figure out how to adapt it slightly, and then we can get uniform interpolation out of it. And yeah, we're just on it, and with my co-authors. And that's pretty much the end of my talk.
Thank you so much, Ian. So questions, remarks, thoughts?